Welcome to the course in Bayesian Machine Learning. My name is Don Brown and I'm in the School of Data Science. And in this video lecture we start our review of probability theory, which is the foundation for this course. We'll look at two major concepts today. The first is the introduction to probability theory, where we'll look at the axioms of probability and some basic definitions, and then we'll look at a fun and interesting historical problem using Bayes' rule. Probability theory is the foundation for what we know of as randomness, which is a key component of the world. It's also a key component of a lot of sciences, including biology, where it's at the foundation of natural selection, and physics, where it's the major foundational component for quantum mechanics. There are two approaches to teaching probability theory. One of them is based on a formal mathematical set of concepts known as measure theory. And the second approach is a heuristic, non-rigorous approach where we use the mathematics of probability to help us build intuition into their use for building models, such as models in machine learning. And this is the approach we will take. There are two definitions of probability. The first one is a frequentist definition, which considers events, probability events, to be defined by the number of times that they occur over a period of time. The second approach is a Bayesian approach, which considers measures of belief as probabilities. So of these two, we obviously, by the name of our course, are going to be using the second. The frequentist approach is actually very restricted because it can only look at events that can reoccur, whereas the Bayesian approach can look at a variety of different events, and as a result is much more applicable to real-world problems. Regardless of the definition of probability used, both rely on the notions of an axiomatic structure to build the formal definition of probability, and that's what we'll look at today. To create this axiomatic structure, we need two concepts. The first concept is that of a sample space, which is simply a set of outcomes. For example, admission to UVA has three outcomes. You're admitted, you're denied admission, or you're put on a wait list. The time until a car has a flat tire, on the other hand, is an infinite number of outcomes spread across the real line in a positive direction from the current time until some time in the future when we get rid of the car. An event is simply a subset of a sample space. So, for example, in the admission to UVA, a subset would be you got admitted to the university. Another one would be you were not admitted, which would include two events. You were put on the wait list or you were denied. Time until a car has a flat tire we think of as subsets of the real line. So, for example, it could be a subset from now until the end of the year, or from the end of June until the end of September. So these are the kinds of things that we look at. We look at subsets of the outcome space as defining events. And it doesn't really matter whether the outcome space is infinite or finite, with a finite number of outcomes. Given those two definitions, we can now look at the axioms of probability. So we have some sample space S and some event, which, as we said, is a subset of this sample space. Then we can define some number, which is a function of the events, and it satisfies the following conditions. The first is that this function is bounded below by 0 and above by 1, so it can take on any of the numbers between 0 and 1. The second axiom is that the function of the entire sample space is equal to 1. And the third axiom is that if we look at any set of events, such as the intersection between two events is empty and the events are not equal to each other, then it's the case that we can look at the union of these events as simply the sum of the function of each of those events. So with these three axioms, it's probably not surprising to you that the function of these events is something that we call the probability. So all it has to do is satisfy these three axioms, and we can define all the rest of the rules that we need in order to build the theory of probability. A very important property derives almost immediately from these axioms, and that's the definition of conditional probability, which is the conditional probability of an event A given an event B, and that's equal to the probability of an event A intersected with the event B. Recall that events are subsets, so we can define their intersection, divided by the probability of the event B. To understand how this works, consider a very simple problem. What is the probability that a family of 2 children, one of which is a girl, has 2 girls? So we can write this as the probability of 2 girls in the family, given that 1 girl is in the family, that the family has at least 1 girl. And that's the intersection of the probability of at least 1 girl in the family with the intersected with a family of 2 girls. And then we divide that by the probability of at least 1 girl in the family. Well, clearly, the intersection of a family with 2 girls with the family of at least 1 girl is simply the probability of 2 girls in the family. And this event occurs 1 out of 4 times for all the 4 possible cases of 2 girls, a boy and a girl and a boy, and a boy and a boy. So 1 out of 4 of those cases is the family with 2 girls. In contrast, a family with at least 1 girl occurs 3/4 of the time, since it can occur in a girl-boy family, a boy-girl family, or a girl-girl family. So when we look at this ratio, it's 1/3, and that's the probability that we were looking for. Okay, another important property that we need to define is statistical independence. Statistical independence is simply the probability that the intersection of 2 events, A and B, is actually equal to the product of the event A and the event B. We sometimes write this, instead of going to the trouble to write the intersection sign with just a comma. That makes it much quicker and easier for us to write these intersected events. And it's easy for you to show, and you should take the time to do it, that given this definition, we can use it with our definition of conditional probability to show then that the probability of A given B is simply the probability of A. So take the time to work through that. In addition to the statistical independence notion, we also need to use the sum rule. The sum rule is very powerful, and it basically tells us that we can find the probability of any event A by looking at the intersection of that probability with an event B over all possible values that B can take on. The sum rule is something we will use a lot in this course, so make sure you understand it. Okay, with these definitions, then we can go ahead and define the most important theorem that we will use, which is Bayes' theorem. And to do that, we're just going to rewrite that sum rule that we just wrote, and we can write it as simply the probability of A is equal to the probability of A in the event B plus the probability of the event A in the event that B doesn't occur. Another way to write that is using conditional probabilities. And again, this is just using our definition of conditional probability to write that joint event of A and B as the probability of A conditioned on B times the probability of B. And in a similar fashion, the probability of A and not B is the probability of A given not B times 1 minus the probability of B. And this again uses our axioms of probability. So we can then write the conditional probability of A given B. This is our definition of conditional probability of A and B divided by the probability of A. Well, we can rewrite that then as the probability of A given B times the probability of B, just using our definition of conditional probability again. So the numerator is changed. This is one form of Bayes' rule. Another form of Bayes' rule uses that definition of the sum rule. So if we apply the sum rule to the denominator, we get the probability of A given B times the probability of B, probability of A given not B, times 1 minus the probability of B. So these two expressions are both Bayes' rule. They're both what we will use and we will describe as Bayes' rule. So again, this is the most important theorem that we have in the class. And it's easy to show that they derive just from the definition of conditional probability and the sum rule. Okay, now let's look at a simple example, but fun example. I shouldn't say it's simple because there's some interesting complicating features of it that illustrate how Bayes' rule works. And this uses what's called the Monty Hall problem. And there's a video on the webpage that describes the game show that this comes from. But basically it came from a very old game show called Let's Make a Deal. Monty Hall was the host of the game show. And in this show, it was a very early TV game show, and it's quite popular. And in this show, Monty Hall gives you a choice of 3 doors. And by you, I mean the contestant. So the contestant gets to choose a door. And basically, behind one of the 3 doors, there's a grand prize, a new car. And behind the other 2 doors are goats. So the question is, you get to pick a door, okay? And then Monty Hall opens one of the remaining doors, and in doing so, he reveals that there's a goat behind that door. The question you have is, should you keep the door, or should you change to the other door that's available to you? So this is the question that Monty Hall proposes to his contestants. And this is easily solved by Bayes' rule. Let's look at one approach. It was a supposedly Bayesian solution, and it was offered by a number of mathematicians and statisticians, actually, at the time that this game show came out. So suppose you choose door 1 and learn that the goat is behind door 3. The question is, should you change doors? And obviously, you would change to door 2. And let A be the award door, so the door that the award is behind. So we can set this up as follows. The probability that the award door is 1, which is the award door that you choose, given that we know it must be behind 1 and 2 because Monty Hall chose 3 and there was a goat behind that. Okay, well, using our Bayes' rule, then that's the probability of the award door being 1 times the probability that the award door is 1 or 2, given that the award door is 1, divided by the probability that the award door is 1 or 2. Okay, so we can look at that as simply 1/3, because the probability that the award door is 1 without any other conditioning is just 1 out of 3. We don't know anything else, so it's a 1/3 chance that it's behind that. The probability that's behind door 1 or 2, given that we know that the award door is 1, is clearly 1, because by definition, that's one of the 2 possible events. And then we divide that by the probability that's in behind door 1 or 2. And again, 2 out of 3 doors, well, that's 2 over 3. So that means the probability is 0.5. So it doesn't matter. So you could either keep the same door or change, and it doesn't matter. Unfortunately, this is completely wrong. This is the wrong way to set up the Bayesian solution. And this gets at the point that in order to apply Bayes' rule, you have to know what you're doing in terms of the events of the problem space. Okay, so let's look at the correct solution. And to get it right, we need to actually define 3 separate events and 3 separate outcome spaces, all of which, well, actually in one outcome space for all 3 of the events. The first event is the same one we saw before, A, the award door. The second one is Monty's selection, which we're going to call M. And the third one is your choice, which you make initially when you start the game, and we're going to call that C. So then what we're looking for, the specific question is asking us for, is the probability that the award door is 1, given that we selected door 1 and that Monty Hall selected door 3. So we can just solve this using Bayes' rule. And notice that in this formulation of Bayes' rule, we've set it up so that in each one of these probabilities, we're conditioning on the fact that we selected door 1, because that's how we started the game, by that selection of door 1. Then we have Monty's selection of door 3, given that we selected door 1 and the award door is 1. And we have, of course, the probability the award door is 1, given that we initially selected door 1. And the denominator, the denominator is given by the probability that Monty selects 3, given that the first selection we made was door 1. Okay, to get the answer to this, then, let's look directly at the denominator. And that's given by this set of events and their probabilities. So notice that in each one, we've got 3 different possibilities here. The award door is behind, the award door is 1, the award door is 2, the award door is 3. And in turn, we have the conditioning events for each one of those. And in every case, it's the probability that Monty chooses door 3, because that's what happened. And again, given that the award door is 1 and that we selected 1. And we can see pretty rapidly what these probabilities are. So again, just concentrate on the denominator in Bayes' rule here and take a look. So the first one is the probability that the award door is 1. And that is just 1/3 because we don't know anything else. So 1 out of 3 possible doors. And notice that that's the same in every case. Probability it's behind door 2, probability it's behind door 3. It's 1/3 in each one of those cases. Now the question is, what's the probability that Monty Hall selected door 3 given that we selected door 1 and the award door is 1? Well, if it's behind 1 and we selected 1, then Monty has only 2 possible choices, 2 choices that he can make, and that's doors 2 and 3. He picked door 3, and the chance that he would do that is 1/2 because there are 2 possibilities, and both doors have a goat behind them, so he could pick either one. In the second case, he's picked door 3. In this case, the award door is 2. We picked 1. Notice that Monty Hall is completely... he has no choice in this case because the only door that has a goat behind it other than the one we picked is door 3. So he has to pick door 3. So the probability of that given, again, constrained by the fact that the award door is 2, is 1. So the probability he picks door 3 is 1. In the last case, it's very simple to see that this is a 0 probability event because if the award door is 3, then Monty Hall picked door 3 and there was a goat behind it. So this is a 0 probability event. It didn't occur. So we can easily zero that one out. Well, okay, once we see what the denominator is, then the numerator is quite easy because the probability that the award door is 1, given that we picked 1, no other information, is again just 1/3 as we saw down here. The probability, and we found this probability as well, the probability that he picks door 3, given that the award door is 1 and we picked 1, well, that's just 1/2 as we saw when we worked out this probability here. So the result then is when we do that multiplication and division, we find that the probability that the award door is the one that we selected initially is only 1/3. So as a result of that, we absolutely should switch doors. So in this game, contestants, regardless of their first choice, the answer is you should always switch doors, which was quite surprising, but it was easily shown. And in fact, over the course of the game show, you could easily see that every contestant, when you looked at the number of times the contestants won when they switched doors, they were twice as likely to win as contestants who kept their same door. And once this was found out, of course, they had to make changes to the game. So there's a fun introduction to Bayes' rule, and next time we'll talk more about other concepts from probability theory. See you then.